So, kind of, why does this chain rule kind of work? Well, there's this relationship of these inside functions to outside functions. And basically, the inside function generates an input that drives the outer function. And then this, we can have multiple layers of this, and then we can have this function f be the input, or the becomes the input that drives the h function. So that the whatever we get out of g drives the F, whatever we get out of here drives the H, and we get this kind of chain going on. So what ends up happening then is, because we have this linking of how this affects the inside to outside, the rates of change are affected accordingly as well. And so this rate of change drives this rate of change, which drives this rate of change. And we can just multiply these rates together. If we actually look at the derivatives, okay, if we call the outside function y, and we call the next inside function u, and the next inside function we call v, the change in y with respect to the next inside function times the derivative of the next inside function times the derivative of the next inside function. Notice that these rates of change are, completely relevant to the inside to outside to inside functions. And not only that, if I'm actually trying to find the rate of change of the outermost function, like in this case h, with the innermost variable x, or dy by dx, notice what happens to all the changes in here. They just all cancel out, and we end up with dy by dx. So this product of the individual rates gives us the overall rate, and algebraically it's very consistent. We can see that algebraically all these rate terms actually cancel out, and we get exactly what we want: the change in the outside function with respect to the change in the innermost function x. Okay, so how does this work? Let's work this out, and we'll break it down into pieces. Again, we're not going to do this as we get better at this. We will be more efficient. We're just going to recognize outside to inside functions. But for now, we're going to be very clear. What are the outside pieces? What are the inside pieces? So here, my outside function is going to be square root of u. Okay, that is the outermost function. The next function, the next innermost function, so that's a cube root, my mistake. This is a cube root function on the outermost side. The next function embedded in there is square root plus 1. Okay, that's the function. It's going to be square root plus 1. That's what happens to whatever we plug into u, we get square root plus 1. And then inside of u, we have the v function, and the v function is just a linear function 2x plus 3. So there's my outermost or innermost functions, and it looks like this. Okay, if I do it in parts, in pieces here, the derivative dy over du. Okay, it's just going to be the derivative of that function. It's going to be 1/3 u to the power negative 2/3. Applying the power rule. Here, the u function is going to be, if I differentiate it, I'm going to get du. I'm going to do it with respect to v. Du by dv is going to be the derivative of the square root function. Okay, so I'm only that u is square root, so the change in square root is 1/2 square root. In this case, it's going to be v. Okay, so that's my change in u with respect to v. And then the innermost function, the change in v with respect to x, the change in the v function with respect to x is just going to be equal to 2. And so if I want to find out the rate of change, well, of change in y over the change in x, I'm just going to multiply dy by du times du by dv. Well, those u's will cancel out, and then times by dv by dx, and the v's cancel out. So my overall rate of change is just the product of this multiplication chain, thus the chain rule. So dy by dx is going to be dy by du times du by dv, this is a u, times dv by dx. Okay, so then what that looks like is this. Okay, so I'm going to multiply that the outside function 1/3, and I'm just going to write it like this: 1/3 cube root u squared. Well, u really is going to be the square root function, so I'm just going to actually replace that back in. This is a square root plus 1 function. Okay? And that represents the inside variable to that function. Okay, so I'm just going to stretch that out like that. So that is my u function right there. And inside the u, sorry, I'm just going to differentiate. So I'm just going to move on. I'm going to not replace the v yet, but the next step is I need to multiply there. That's my dy by du. I need to multiply by du by dv. So it's going to be like this: 1/2 square root whatever the v function is, times the derivative of v by dx, which is times by 2. So this is what it looks like when I've actually started using the functions instead of the notation. And what I can do is if I can recognize the functions embedded, I can just keep that in there as I do my derivatives. So just the outside function differentiated, I have my 2 inner functions untouched. The next layer function differentiated, then that inner layer untouched, and then the next layer goes to just the derivative of the innermost function. And again, this gives me these pieces algebraically they're consistent. The derivative of the composite function really is just a product of the chain of outside to inside derivatives.